Welcome everyone to this new webinar of the Grade2XL project. Today we will talk about the principles of absolute environmental sustainability assessment with two experts from DTU, Denmark Technical University. But before we dig into the topic with them, let me just introduce very briefly the Grade2XL project. Grade2XL is a European project funded by the Horizon 2020 program. It was launched already 4 years ago in March 2020, and we are now heading to the end of the project that will finish next August. It gathers 21 partners in 8 different countries throughout Europe. Gathering academics, but also industrials, working together on the acceleration of the development of an industrial uptake of the multi-material WAAM technology. The project is focusing on delivering 8 demonstrators for different industrial applications. Among them, we have a mobile ring for hydroelectric plants, molds for composites or plastic injection, and also a boat propeller, which will be the use case that will be discussed today by our experts. So I'm very pleased now to introduce our 2 speakers of the day, which are members of the Grade2XL consortium, so both working at DTU. So the first speaker will be Michael Hauschild. Michael is a professor in life cycle assessment at the Department of Environmental and Resource Engineering at DTU. Michael has been overall responsible for the department's life cycle engineering research activities, teaching and professional training for more than 10 years. Together with colleagues, he developed and documented one of the first full life cycle assessment methods and has since been part of the international research community on life cycle assessment. Lately, he has been mainly responsible for developing the absolute environmental sustainability assessment framework and methods, and heads the DTU Center for Absolute Sustainability. So thanks, Michael, for being here with us today. And our second speaker of the day is Stig Irving Olsen, who is Associate Professor in Sustainable Manufacturing at the Department of Environmental and Resource Engineering at DTU. His research in the past decades focused on assessment of life cycle environmental, social, and resource impacts in specific industrial applications. And use of life cycle assessment, LCA, in decision support, circular economy, sustainability assessment of emerging technologies, such as WAAM. His current research focuses on application and operationalization of new methods for sustainability management, often in relation to new technologies. So now I will leave the floor to Michael for the first presentation entitled Planetary Boundaries and Absolute Environmental Sustainability Assessment. And just for information, you can leave your question in the chat and we will take the questions at the end of each presentation. Thank you. Michael, I let you share your slides. No, you don't have the micro, Michael.
Thank you very much. I'll just see if I can share the right screen. So you see my presentation now?
Yes.
Perfect. Good. Thank you very much for this opportunity to talk about a topic that is very close to my heart. Together with Stig Olsen, we've decided to share the presentations between us so that I will first introduce first the planetary boundaries, and then which is a concept for absolute environmental sustainability, and then the principles of how to assess sustainability in absolute terms. So if we embark at it with the planetary boundaries, we can say that this slide in a way is the starting point for the development of the planetary boundaries originally. It's showing the development in the temperature of the atmosphere over the last 100,000 years up to today. That's what you have on the x-axis, the age before present. And then on the y-axis, you have the temperature at that point in time, how it was relative to today. So you can see that it has been very strongly fluctuating, the temperature over the last 100,000 years. This is mainly during the last glaciation, but we've seen changes of up to 15 degrees within very short time, maybe a century. And right now we're discussing whether we are at 1.2 or 1.3 degrees above pre-industrial levels. But this has been an extremely unstable climate until the onset of the Holocene, which is the geological epoch since the last glaciation, where temperatures have been remarkably constant. And above the graph, you see points in the propagation of humans over the planet. So from the first migration of the fully modern humans out of Africa, our species of humans, so Homo sapiens, is believed to have evolved something like 250,000 years ago in Africa, southern part of Africa, and around 6,000 years ago, there are indications of a larger migration out of Africa of Homo sapiens, and then gradually propagating over the planet under this very unstable temperature regime. They've been living as hunter-gatherers at that time, but after the stabilization of the climate, after the glaciation in the Holocene, their numbers has no doubt increased a lot, and we see the beginning of agriculture around 8,000 years ago in multiple locations of the planet at the same time, more or less. And we also see the evolution of all the great human civilizations, not just European, as the graphs or slide says, but all human civilizations, also Asian civilization, African and American civilizations are all within this period. And we see a growth in the global population from somewhere in the 10 or 100,000 globally, probably, to now 8.2 billion people. Now, if you look at a slide like this or a graph like this, you will notice that the very, very stable climate that we have now and have enjoyed during the Holocene is not a given thing. Actually, if you look at this graph, you would say the normal situation on the planet is a very unstable climate. And this is also the case much before this 100,000 years ago. So something happened after the last ice age that stabilized the climate. And we're not completely able to explain what, but whatever it was, it is not something we want to disturb with the risk of bringing us back to what could, from this graph, seem to be the normal situation with a very fluctuating climate. You can just think about the challenges we've been facing over the last years due to 1.3, 1.4 degrees above pre-industrial levels temperature. And then imagine what it would be like with 8.2 billion people on the planet and not 100,000 hunter-gatherers just moving around and trying to escape the cold or escape the rising water or whatever. It's been very, very challenging way to live here. We don't want to disturb it, but how can we avoid that? Well, it would be nice to know what it is we shouldn't disturb, of course. And there was a group of researchers around Stockholm Resilience Center that identified 9 Earth system processes that they believe are important for this stable situation we have with the climate during the Holocene. And one of them, of course, is our pollution of the atmosphere with greenhouse gases. So that's the one that is in this spiderweb diagram called climate change. But you see there are many other processes involved, or they call them processes, I would say properties perhaps. So you have the integrity of the biosphere as super important. It's clear that a big change from the Ice Age till now is that a much larger part of the planet's surface is covered now by biosystems, or sorry, ecosystems. So you have multiple thriving ecosystems over most of the planet. So during the Ice Age, maybe 2/3 of the planet was covered by ice, and now it's maybe 10% or something like that. So there's a huge growth, a huge change, huge increase in biological activity. And this research group around Stockholm Resilience Center speculate that this is part of the explanation, and they're identifying processes that are important to keep this situation, to avoid disturbing the situation. So apart from our emission of greenhouse gases, it is also our use of land, our use of water, our manipulation of biogeochemical flows, phosphorus and nitrogen, and so forth. Novel entities at the top is the introduction of chemicals, or the disturbance of the natural level, if you like, of metals, but chemicals, plastics, things like that are not naturally in the environment and that we introduce. That's the concern there. And for each of these processes, they operated with a model where you have on the x-axis a measure of the pressure that we exert on the environment, and that is represented by a control variable. If we were talking about climate change, it could, for instance, be the concentration of CO2 in the atmosphere. So we see an increasing pressure as we move right on the x-axis. And then on a y-axis, we have a representation of the state of the environment. So how does the environment respond to our pressure? And you can see that as long as our pressure is within the green zone on this graph, there's no real response. So there's a resilience, if you like. There's an ability to adapt our pressure without really causing any major changes in the state of the environment. But there can be thresholds, and when we're talking climate change, there are indeed tipping points that have been speculated. At least we don't know. We haven't passed them yet, but models predict they are there, and we can see signs in historical data that they have been exceeded, in very early past times. And we don't want to exceed these thresholds, because when we do, you can see there's a big change. So even for a small increase in pressure, we see a big change in the state of the environment. So we're talking about tipping point for the climate, for instance, and this is the rationale behind the Paris Agreement's ambition of keeping the temperature, the human-made temperature increase not higher than 1.5 degrees above pre-industrial levels. That's to say, okay, if we manage to do that, we will probably not pass any thresholds. Now, we don't know exactly at what value of the control variable this threshold lies. There's an uncertainty around it. I think this is model predicted. And the uncertainty range is the yellowish zone that you see on the graph on the right side here. And at the lower boundary or lower level of that uncertainty range, this group of researchers define the planetary boundary. So their rationale is that as long as we do not exceed the planetary boundary, we are quite sure that we have not passed the threshold. But the moment that we move into the yellow zone, we could in principle have passed the threshold. We don't know, because we don't know exactly where it is. But of course, the higher the pressure, the more we move into the yellow zone, the larger the probability that we have passed it. And indeed, when we move into the red zone, we are quite sure we have passed that threshold. And they identify this kind of boundaries, as you can see, for all these 9 processes on the spiderweb diagram to the left, and also identify our current state. Where are we? And if we look at the historic data from the first publication on this in 2009, where 3 boundaries were crossed according to their assessments at the time, to 2015, and of course some of them there was no sign. I mean, the novel entities, for instance, they were not able to quantify atmospheric aerosol loading, also not freshwater. These were the 2 mains that were not quantified at the time. To 2015, well, 4 boundaries are crossed, and now to 2023, a recently published paper where 6 boundaries have been crossed, and they're now able to actually quantify all of them, all 9 boundaries. You can say the development is critical, and this is the foundation of our definition of absolute sustainability. Because if you think about the definition of a sustainable development as it was proposed by the Brundtland Commission, United Nations Commission on Environment and Development back in the 1980s, A sustainable development is a development that meets the needs of the present without compromising the ability of future generations to meet their own needs. That's the focus of it, right? Meeting needs of ourselves today, but also allowing our children and their children to meet their needs. That doesn't really say anything about what needs can we expect to get met, what is needs and what is wants and so forth. So there's a lot of ambiguity in here. And what this offers is really an absolute take on saying, well, whatever the needs are, here are the constraints that we need to operate inside. We cannot allow that we exceed the planetary boundaries, consistently. We need to find ways of living that allow us to live within what is here called the safe operating space, the green zone. So we define absolute sustainability, paraphrasing the Brundtland Commission, as meeting the needs of present and future generations within the biophysical boundaries of our climate and ecosystems. It means within this safe operating space. So we take, you can say, these biophysical boundaries, which, if we don't respect them, we have the risk of runaway situations with the climate. But also the big crisis we're facing is actually a biodiversity crisis. We are losing species globally at rates that have only been seen 5 times before in the history of the planet. We're talking about mass extinction periods, which is when within a relatively short period of time, suddenly a lot of species disappear that were there before. And the last 5th mass extinction episode was around 65 million years ago, when the dinosaurs became extinct. And they're talking about now that we are losing species with rates that have been seen these 5 times before, but we are actually at the moment in the middle of the 6th mass extinction episode in the history of the planet, that at least that is known. We're losing species that rapidly, and this time the reason is not an asteroid collision, but it's us, the humans. It's our use of land, appropriation of space, basically. So, summarizing, you can say the planetary boundaries are examples of limits for our pressure on Earth system processes. And the focus of the planetary boundaries is climate stability. They cover many types of environmental impact, but the core of them is the climate change and the biosphere integrity processes. And absolute sustainability we define as meeting the needs of present and future generations while respecting the planet's biophysical boundaries. So what does that mean? How can we measure it? And why is it important to measure it? Let me introduce you to the concept of eco-efficiency. Eco-efficiency is a measure of how well, if we talk about eco-efficiency of a technology, for instance, the technology that Stig will be presenting shortly for WAAM, the WAAM technology for producing boat propellers. The eco-efficiency for a technology like that is defined as the ratio between the service that the technology delivers to us and the environmental impact that it causes when it delivers that. And I'd like you to ignore just the 1/T. It's not relevant in our context here. But eco-efficiency is what we need to aim for. We need to improve eco-efficiency. We need to develop technologies that allow us to meet our needs with much, much lower environmental impact, as we just saw. We are exceeding boundaries in many locations. We need to do it better. Eco-efficiency we determine that with the tool, the method life cycle assessment, LCA. And as I said, it has to grow very strongly to achieve the needed reduction in environmental impact. Now, life cycle assessment supports assessments of eco-efficiency. Do we, by using WAAM, achieve our function to produce a boat propeller, for instance, with less environmental impact, more eco-efficiency than if we use the conventional casting and grinding and so forth, or turning. Same or higher functionality with less environmental impact. So on a scale from higher to lower impact, do we move in this direction? So is it more sustainable than the alternative? But we increasingly understand that we also need to know whether it's sustainable, not just more sustainable. So the reference is not necessarily some other technology. It's of course useful to know, are we moving in the right direction? Are we doing things better? But we also need to know whether we are doing them good enough. So where's I mean, are they both sustainable? Is none of them sustainable? Is the green sustainable? The blue is not? Where's the boundary beyond which the activity becomes unsustainable? And in order to evaluate that, we've developed in the international sustainability assessment community a method for absolute environmental sustainability assessment. It's abbreviated AESA. AESA builds on LCA. So like in life cycle assessment, we take a full life cycle perspective. That means we are going from the extraction of raw materials over the production of components, the manufacturing of the product, distribution, transport is in here, use, maintenance, and end-of-life treatment, possibly reuse, recycling, and so forth. So we're looking at the full life cycle, and we're considering all relevant environmental impacts. You saw with the planetary boundaries before, 9 different impacts, and we have some other impacts as well that we're operating with in traditional life cycle assessment, LCA, that are not necessarily closely linked with the climate as these other ones are, but perhaps with human health or resources or things like that. So we need to look at all of them. And then what we do is we identify the biophysical boundaries and we determine the safe operating space. So in the example with the planetary boundaries, the green, how large is that? What is the size of the safe operating space? And when we've done that and we want to assess whether our technology is sustainable or our ways of delivering this service that we are looking at, and I mean, I have the example with the boat propeller, but it can be anything. It could be fulfill the nutritional requirements of a population, transport the citizens of Paris from home to work every day for a year. You know, whatever the service is, we can do it in different ways, and we compare whether one is more sustainable than the other. But here we want to know also, is any of them sustainable in absolute terms? And sustainable in absolute terms means that it performs the service with an impact that lies within its share of the safe operating space, because we need to find out how large a share of the safe operating space, of the green space here, belongs to our service. So how can we allocate the safe operating space to different activities that we want to perform? We want to have nutrition, food, we want to have housing, we want transportation, and so forth. How can we allocate it? And there are many different principles for that. So in principle, you have the boundaries at a global or regional level. You can allocate them down to a person, and then you can upscale them to the level of a company, a product, a service, an activity, a sector, household, nation, whatever. And the principles that we're using for that, there are many, and they reflect different ethical norms. And I'll not talk about all of them, but just introduce you to some of the thinking in them, and then specifically focus on the ones that Stig will be using in his example. But the first one is equal per capita. And that's basically saying, okay, we have globally this space. We are 8.2 billion people on the planet. We share it evenly between us. So how much is that per person? And then each of us have a space, a certain amount of CO2 equivalents, climate change, for instance, or whatever it is. And we can then decide how do we want to spend that. A little bit like a budget, an economic budget, you could say. So that could be one way of sharing it. Another one could be, yeah, but maybe we shouldn't have all the same space because some of us need more space than others. Certainly, if we go at the societal level, you can say, well, we have perhaps better facilities for reducing. There are countries that have not yet built up their health infrastructure, transportation infrastructure, whatever, which we have in the wealthy European part of the world. So maybe developing regions, the global south, should actually have a larger space per person than we have, because we've already used a part of our space for climate change, but we have also used some of it to build these facilities that we need in order to live in a socially sustainable way. And I'll just jump on to the next two ones, the grandfathering and the economic value added, which are the two that are used in the example that you will see in a little while. Grandfathering is where you assign share proportionally to the environmental impact that the activity has in a reference year. So if a certain activity, let's say cement production, has a share of the total pollution. So the total climate change, let's say 1% comes from cement production globally. Then it means that cement production gets 1% of the space, also the reduced space. So when everybody needs to reduce by 50% in 2030, the cement factory still has 1% in 2030 of the total space, but of course a reduced space. So the grandfathering here means that you get a space that is proportional to your share in the problem today. This is actually used in one of these absolute sustainability assessment approaches that are out there. The science-based targets, you may have heard about it. It's where companies commit themselves to reducing their impacts according to the Paris Agreement, and their grandfathering is used to determine what is the space that each company has. Another approach is economic value added, where you assign a space according to the activity's share in the total economy. So if this activity, let's say cement production again, if cement production is 2% of the global economy, cement production gets 2% of the space. Okay, these were two principles, and these are the ones you'll see used in the next example. So let me just summarize here. When you perform an AESA, an absolute environmental sustainability assessment, you first identify where are the biophysical boundaries that we need to respect in order to avoid risking runaway situations in climate or biodiversity. And then based on that, how big is the safe operating space? And then you determine how you allocate the safe operating space to different activities, and particularly to the activity that you are studying. And then you calculate the impact profile of your activity using life cycle assessment. So how big are the impacts actually? So now you know what's the space that it can claim, and then you can say, okay, what space does it take? And then you compare the two, the impact that it causes and the allocated space. And if the impact is larger than the allocated space, it is not sustainable. If it is smaller than the allocated space, it is sustainable, with the conditions, the assumptions that you have made during your assessment. So let me summarize my part here. Absolute environmental sustainability assessment builds on LCA, which is a very well-developed international standardized method. ISO standards exist and so forth. 50 years of history. AESA is a young discipline, and it relates the environmental impacts to the assigned space, operating space, to measure whether the activity we're talking about is sustainable or not. It covers all relevant environmental impacts. That's very important as well, a fundamental of LCA. Okay, that concludes my presentation. So I'm not sharing anymore, I guess. And I'll be happy to take any questions that may have come up.
Lucy, you have the comments, but you were muted.
Yeah, I was. Yeah, sorry, I realized I was muted. Yeah, thanks, Michael, for the very, very excellent presentation and introduction to the concept of absolute sustainability and of the methodology of AESA. For the participants, if you have any questions for Michael, you can just either speak or put them in the chat. Or you can also ask your questions at the very end of the webinar, and maybe we go on with Stig with your particular use case of the bot propeller. Stig, I let you share your screen.
Yes. I think I'm sharing now, right?
Yeah, we can see it. Thank you.
Yeah, good. Yeah, actually, it's mainly my one of the PhD students actually working on this Grade2XL project, Valentina, who has prepared most of the work for this presentation. So that's why she's first in line here for this presentation. So I'm going to share a specific application of this absolute environmental absolute sustainability assessment, absolute environmental sustainability assessment for a boat propeller, which is one of the demonstrators, as Lucy just said, for this Grade2XL project. The boat propeller is produced by WAAM. And just to put it into context, we have a manufacturing sector where we have a huge carbon footprint, and the steel is very much part of that, actually. Let's see, they have about 25% of the industrial carbon emissions are related to steel production. And what can WAAM contribute here, or wire arc additive manufacturing? Well, a lot of the contribution from steel is, of course, by the production of steel, because just in the process, by coking or by processing with coke, we get emissions of carbon dioxide, but also in the processing of the steel into different products, we can have a lot of emissions here. So wire arc additive manufacturing can contribute by using less steel, making say the products more lean, optimize the weight of the products, etc. So by this 3D printing. So we have some potentials for using WAAM in the to reduce here. So the original thought with this study was actually to investigate how wire arc additive manufacturing combined with circular economy strategies influence flow and sustainability of primary and secondary materials used for product fabrication. What I'll be more precisely about in this presentation is how these methods and strategies can contribute to absolute sustainability, if they can at all. So when you look at what are we doing here, we're going to have some goal and scope definition and inventory. We're going to do a lifetime impact assessment related to the planetary boundaries, and then a little bit of interpretation. But I will not do this dynamic material flow analysis, which has been part of the study originally. So the functional unit for this study was actually the yearly global use of marine propellers for average fishing vessels, so up to 25 meters. So that's a medium-size fishing vessel. And as you can see here in this, the scope of the, we have the temporal scope 2050 to 2050, 2015 to 2050, and we assume that there will be a substitution of the traditional casting of the propellers will be substituted by wire arc additive manufacturing by a rate of 1.26% per year from 2027 to 2050. So a kind of a gradual increase of the use of wire arc additive manufacturing. And as you can see here, we have the blue ones related to wire arc additive manufacturing. So we have some Inconel, which is a very hard surface layer, the stainless steel. We have a core steel, which is then coated by Inconel, and we have the boat propeller produced by this WAAM. That is compared to the traditional way of producing, where we just cast copper alloy and use it for a boat propeller. In both cases, there will be some scrap production, which goes into a scrap preparation, and this will go back into the production again, which is called this a closed loop recycling. Some part of at the end of the study or end of use of the propeller, you will see also that metal waste will be recycled and will be produced in an open loop recycling, production of primary copper or production of stainless steel, and substitute that. So geographical scope is the world, And the WAAM strategies will be that we have a lifetime extension of the propeller by using this hard layer of Inconel, a lifetime extension of 9 years. And because we can actually, as I said before, when we use this 3D printing, we can optimize the design of the product. And at least from the partners of the project who are who is producing the propeller, they have an estimate that they can actually reduce fuel consumption about 0.1% due to this optimized design of the boat propeller during the use stage of the fishing vessel. And that turns out to be a very important part of the overall system here. So just very say more simplified, we have the business as usual scenario 1, where we have this casting, but in an open loop, meaning that the bronze after the use of the propeller will go into producing of copper used in other products, or we have a bronze alloy casting in a closed loop where it actually goes back and be used by in the propeller. And then the WAAM scenario would be, of course, partly the open loop and partly a steel and Inconel closed loop use of that. So these are the scenarios. So what is the absolute sustainability perspective that we are looking at? Yeah, to look at it from an overall perspective, you would say, doing life cycle impact assessment, we actually could calculate the impact score of different activities by summing up the mass flow of a specific substance and multiplying it by the characterization factor of that substance. Meaning that, for example, taking the example of carbon dioxide equivalents, we will have a characterization factor here would be 1 for carbon dioxide, but methane, which is about 25 times more potent climate gas than carbon dioxide, would have a characterization factor of 25. So this is how we normally do this in life cycle impact assessment. So what we are looking at when we talk about the absolute sustainability perspective would be the planetary boundaries. And the planetary boundaries for climate change has been calculated by 2 different ways. One is the concentration of carbon dioxide in ppm, carbon dioxide per year kilogram. And we have an energy imbalance of CO2, which is the watt per square meter per year per kilogram. These are related to the ways that the climate change has been calculated in the planetary boundaries. So we go down to how do we actually then downscale the safe operating space? We downscale the safe operating space here to a product by giving it the assigned share, as Michael just said, and multiply that by the full safe operating space. And to be more precise about that, I'll come into the next slide and present exactly how did we do that. But just briefly to say, well, Michael just showed all the different sharing principles we have for how do we share the safe operating space. And we have been using in this study the grandfathering, which is where we say the assigned share is proportional with the environmental impact in the reference year. So how much did propellers, how much was their impact in 2018, which was the reference year that we used here. And the other principle we have used is the economic value added, or actually we use the gross value added, where we have say the assigned share is proportional to the gross value added by the propeller. And how do we calculate that? We'll come back to that in the next slide. So, as Michael said, the planetary boundaries and the absolute environmental sustainability assessment in principle covers all the environmental impacts, and we should. But we, for the example's sake here, we just look at the climate change. So we focus only on climate change here, do not take into account all the other impact or planetary boundaries. So we look at the climate change, the CC here. So the share of the safe operating space taken up by the product is the full safe operating space. So how much CO2 can we emit to the atmosphere in 1 year as a whole global society. So and what is the share then from our product here? What is the share of that? And we calculate that by the two different principles as mentioned. One is the gross value added, where we say the factor here or the sharing allocation share would be the gross value at the overall global economy, the gross value added per year in 2018. And we have then the gross value added of a propeller in 2018. So this is, of course, a very small share. In this case, we're about 10 to the minus fifth would be the share here, which makes sense that it should, of course, propellers to make up a very small part of the overall gross value added in the global economy. The other principle being used here is the grandfathering, where we put in the allocation or the share here would be the impact of our propeller in a given year on climate change divided by the overall impact on climate change in the world in 2018. And this is per kilogram of propeller. We have, or per ton of propeller, this has been calculated. So you can say the occupied share of the safe operating space here by the propeller is calculated by the impact score times the flows, which were calculated now by this dynamic mass flow analysis, divided by the share of the safe operating space calculated here. I don't know if this makes sense, but you can ask questions afterwards. So, but how does this look then for our propellers? We have here is the grandfathering. So looking at how much, if we look at how much impact does it have already, and give it corresponding to that, we see that the use stage up here transgressed the planetary boundaries already from the beginning. And it's the use phase of both all the scenarios we have been looking at. It's being transgressed here. But if we only look at and that's part of the use phase, right? So that's the fuel used mainly the fuel used to drive the fishing vessels, which is responsible for this up here. If we look at this part here, it's the purple one is the materials and manufacturing for WAAM, whereas the red one is the materials and manufacturing for the business as usual. And they are overlying each other actually. So we see that for the materials and manufacturing part, the WAAM actually is a little bit worse than the business as usual. And we will see that they would transgress the planetary boundary in about 2037 or something like that. Okay, so we did some sensitivity scenarios with propulsive efficiency and WAAM with the gross value added. And so if we look at the gross value added here, we can see that if we use the gross value added, we will see that in about 2025, the two business as usual scenarios will exceed the planetary boundaries for climate change, whereas the WAAM would exceed it a little bit later. And that's because of the extra efficiency of propulsion by the optimized design of the propeller. We also see still that the manufacturing and materials would not transgress the planetary boundaries, and that we will have kind of a negative contribution by the disposal stage, so the recycling will actually contribute to less impact on the climate change. So I think this was the overall presentation that I had. Yeah.
Thanks a lot, Stig. Thanks a lot. This is a very complex topic, but extremely interesting. I don't know if any of the participants has a question either for Stig or for Michael. I don't see any question in the chat.
No, don't seem so. No.
So in that case, we may. Someone wants to say something? No. In that case, I think we can just conclude. I will have just a few updates to share.
That's fine, and you're welcome to share the slides as well.
Okay, thanks a lot. We will make indeed it's not. I will make the replay available as well. I wanted to share. Sorry, my final slides just to announce a couple of events. All right, can you see the slides? Yeah.
Yeah.
So yeah, thanks a lot to our two speakers of the day. So we will make the replay and the slides available. And I wanted to announce also the two next Grade2XL webinars. Save the date. The next one will be on the 12th of April with partners from CEA. And we will talk this time about non-destructive testing for additive manufacturing of metal parts. And the next one will be, on the 21st of June about the TO methodology with a design tool in an industrial setting by our partners from M2I. So we will soon also communicate about these two events. So feel free to register as well. And also for the people in the Nantes area, next week there is a FADAP meetup technical day about additive manufacturing organized by Nantes University. and Grade2XL will be also present there with the booth. There will be also another event about metal additive manufacturing at the end of March 28th with a presentation from Naval Group, with also a partner from Grade2XL on this occasion. So this is again an event organized by a Nantes University. And at the European level, on the 9th of April, there is an online event that is open to any contributors from the regions that are part of the Vanguard Initiative 3D printing pilot. I invite you to get in touch with me if you are interested. This is a very interesting network gathering the supply and demand of 3D printing services throughout Europe, and they organize this online event, and there is a call for pitches open. So if you are looking for a solution, if you have a service to offer in the field of 3D printing, this is a very good opportunity to give you some visibility. And last event I have to announce for today is the international conference in welding that is organized in Rhodes in Greece in July, and the Grade2XL project will be associated to this event. We will have dedicated sessions to present the final results of the Grade2XL project. And as always, you can visit our website. You can get in touch with me if you want to know more, to get in touch with the partners from Grade2XL, and you can follow us on LinkedIn.